This equation seems pretty ridiculous. I mean, given that big O measures how long algorithms take to run, how could we ever ignore a constant factor this big? Well, because that previous statement was wrong on multiple levels. Big O doesn't measure anything, and it was actually first used by a gentleman named Bachmann, Paul Bachmann, in 1894, about 50 years before modern electronic computers even existed. So that raises a question. If Big O was not originally about algorithms or computers, what was it about? Answering that question will lead us to understand why Big O ignores constant factors. So Big O originally was about functions, and specifically it's about how we can define different classes or specifically sets of functions that grow faster or slower than other functions in some deep, fundamental way. So to show this, I've got 4 functions, f of n, g of n, h of n, and I of n, and I'm not going to tell you what those are for now. Instead, I've got these little animated tiles that show what the output of each function is for some given value of n. And as I increase n, which you'll see in a minute, these tiles sort of flip over or unfold to show how each function grows. Now, as you watch these tiles flip over, when I increase n, I need you to pay attention to one key question. Which 2 functions are really most similar in terms of how they grow? So now I'll double n to 4 and then to 8. To be clear, there's nothing special about doubling. I'm just sort of making a large increase in n to more vividly show how these functions grow in different ways. And as you watch them grow again, or watch them unfold, answer the key question, which 2 are really most similar in terms of how they grow. So in terms of how these grow, shown here as a sort of unfolding, you can really see that f of n and I of n grow in the same way. They both sort of unfold one time. And the other ones don't do that. Now this unfolding one time, it shows that they double. When you double the input n, the output also doubles. That's what I of n and f of n both do, even though I of n is of course much bigger. And g of n and h of n don't behave that way at all when I double the input value of n. G of n actually unfolds 3 of itself, which in total means it gets sort of 4 copies, it quadruples whenever I double n. And h of n is very different. H of n whenever I double n just increases by 1. Here's the actual functions if you're curious. So now you can see that I of n is 50 times bigger than f of n. But despite that, they have this distinct similarity in terms of how they grow. And capturing similarities like that is what big O, big theta, and the other asymptotics are really about. But how can I capture this? So let's have a group called R functions. And we're going to put I of n and f of n in there, but you can also put functions like 3n or 4n or 1/2 n into R group. For all of these, when you double n, the output's going to double, as we saw with the animations. Now there's other functions that are almost like this, stuff like n minus 10 or 3n plus 4, and as n becomes large, these functions will also roughly double when I double the input. And there's even stuff like n minus square root of n, where when n becomes big enough, it's going to behave in more or less the same way. So those go in our group as well. But we want to more rigorously define our group. How could we do that? So how about we take some constant c and some function p of n that may or may not go in our group. And we're going to say that if p of n is less than or equal to c times n, then it gets to go in our group. In this context, we don't really care about negative numbers. So I'm going to tack on a 0 less than or equal to kind of show we're not worried about what happens with negative numbers. And do we want this inequality to be true for, n equals 1 but nothing else? No, what we really want it to be true for is n up to infinity, but maybe it's only true beyond some certain point. A lot of functions kind of behave differently for n equals 0 or n equals 1, but maybe when we go beyond some point, they're going to fit this definition. And so we can call that critical point that we have to go beyond n naught or n sub 0. So this last part of the definition basically captures what people mean when they say for sufficiently large n. It just means all n beyond some n naught, and we have to say specifically what n naught is. We also have to say what c is. But this quick inequality we've built to represent what functions go in our group, this is really what big O is. At least it's what big O is for the simple linear function n. Now if we generalize this to be any function g of n, not just the simple linear one, and we write it up in a nice fancy way, we get this. This is the textbook definition of big O. You're welcome to pause and read this if you'd like. Did you pause and read it? If you did, tell me in the comments. I would love if at least one person actually paused to read the definition. If you didn't, that's okay. This is YouTube. Some of you are probably eating a bowl of soup right now. Whatever, I do it too. So let's take a closer look at certain aspects of this definition. These curly brackets on the side define a set. And here it's actually going to be an infinite set because we can have stuff like 1.1n, 1.11n, 1.12n, and so on. And this is the definition that we use in computer science. Paul Bachmann, the 19th century mathematician who came up with this, he had a different definition based on limits, but it largely captures the same idea. Now this part of the definition that says there exists C is critical. What this is saying in terms of using this definition is that we get to choose a different C to make different functions fit into our group. And being able to choose a constant in this way is what allows this definition to encompass many different functions that grow in this manner. Choosing this constant C is how we put functions like 2n and 2000n into the same group. And we want to be able to put them into the same set, again because this is not really about which function's bigger, it's about how they grow, and 2n and 2000n grow in a very similar way. Now if you go back to our functions from earlier, you remember that f of n and I of n were the two I said grew in a distinctly similar way. Looking at f of n, which could represent the runtime of an algorithm realistically, we could choose c to be 2 or 3 or 4, whatever, they'll all work, and n naught to be 0. Then f of n satisfies this inequality, so it fits the definition and it can go into the set O of n. We can do the same thing with I of n. Just choose c to be 100, the same idea applies. Now some of you who are really paying attention might notice that I can also get h of n into my group. I can choose c to be 10, then h of n meets the inequality, and I can stick this log n plus 5 into my group. Now that probably surprises some of you, but O of n, as it's defined in a textbook, is just an upper bound. It doesn't have to be a tight upper bound, so I can put stuff that's definitely less than some linear function, like log n, into my group. Now if you wanted to exclude stuff like log n or constants or square root of n from our set, you would have to use big theta. And if you don't know big theta, I do offer tutoring services. If you have to learn it for a course or something, check my link in the description, or I've got more videos coming about that, so go ahead and subscribe. So now we're ready to look at the problem we started with from a new angle. So what exactly does this mean? 999 times O of n equals O of n. Well, there's some funniness going on with the notation here. These O of n's don't refer to one specific function. In this context, what they mean is each O of n is just some function from the set big O of n. Now we don't know what these functions are, and they could be the same function or different functions, but we do know that both functions have to fit the definition. So what this is really saying is 999 times some function from O of n equals some function from O of n. But is that actually true? Let's find out. Call this function on the left side p of n. Because p of n is from O of n, we know that it satisfies this inequality for some c and n naught. Now we don't know what C and N naught are, but we know they have to exist. So let's just take this inequality and we're going to multiply the whole thing by 999. Now we have that 999 times P of n is less than 999 times C times n. We're going to do a couple quick substitutions to get this into a form that will also fit the inequality from the definition. We're going to call 999 times C, C2. And we've got 999 times some P of n is less than or equal to our constant C2 times n. Now we're going to call 999 times P of n Q of n. And I'll make that substitution in the top as well. Now in the inequality, it certainly looks like Q of n fits the definition of big O. We have our constant multiplier that we need for the definition is of course C2, and we can use the same n naught from earlier. So Q of n also fits the definition. Therefore, Q of n is also in O of n. And because Q of n is just some function from O of n, we can replace Q of n up top with O of n. And now you can see that this equation makes perfect sense. There's also another way to read this equation we started with. Whenever you see big O or big theta or something like that by itself on the right side of an equal sign, you can actually interpret that equal sign as kind of indicating set membership. So what this starting equation really says, read in that simpler way, is 999 times some equation from O of n is also in O of n. I hope now you see why that's true, and moreover, why we'd want that to be true. Changing the constant multiplier doesn't change the way functions grow in some deeper way, and when we're analyzing algorithms, we don't often run into stuff like 999 anyway. I hope you enjoyed the video. Thank you for watching.